looking at section 3.4, it is all hinged on your understanding of this composite function idea. So this is where all that work we did on reviewing algebra, and I had you going through chapter 1 on your own to help you refresh on some of those algebra skills and concepts. We talked in class together about composite functions, and now is where we really do need to have an understanding of them. If we are looking at, let me just throw out f of x. I'm not going to tell you what f of x equals. G of x, I'm not going to tell you what g of x equals. What I want you to do, though, is what's one way that you can use f of x and g of x in a way to show h of x as a composite function. So take a moment and do that. Okay, so let's see what we came up with. Heather, what's one way that you wrote? Do you know what a composite function is? Okay, we have to know that in order to go further in here. Heather, what about you? Okay, f of g of x. Okay, that's one way we could do that. Let's take a look at this. What we have then is this whole thing of g of x. Now, in our discussion, in our function f of x, what is the role? What is the responsibility? What is the name, or that we give g of x? In function f, it's known as the what? Excuse me. The what? Yeah, so this is the input. In function f, it's the input in f. It happens, though, to be that's the output of g. Okay, so I'll put that in green here. So if I kind of border this in green here, then we can say that it is the output of function g. So that notation, as we've gone through before, tells me that g of x plays double role. Again, in its own function, it represents an output, but when we place it inside the function f, and notice I use the word inside, because we're going to be talking about inside and outside. The inside function of this composite function is g of x. Now, again, as a composite function, I know when we talked about this early in the semester, the way that I usually talk about to students is that I ask you, and maybe you remember this, within the last 8 hours or so, how did you successfully use a composite function? Now, initially, I know some of you are saying, well, can't. I didn't use f of x and g of x and numbers and letters. But think about what a composite function is. I take an action. By the way, what's the role of x and g of x? It's the input. So I start with I have an action g that I begin with, put something in, and I get something out. And what I get out of it is g of x. And then I take that result, I put that as the input into my second action, and so where I left off with g of x is my starting point for the action f of x. So in the last 8 hours, where did you successfully use a composite function? And usually about this time of the year, it's easier to look around and say, it looks like everyone did it successfully. I don't see any socks over your shoes. Okay, so the first action is get a pair of socks, and the output of that is they're on my feet. My second action starts with I've got socks on my feet, and the output is put shoes on. Now, can you put shoes on before you put socks on? Not if you're going to do it correctly, right? And so that's the idea of a composite function. You start with one action, starting point, input, get an output, and that output becomes the starting point for the second one. Again, we have to understand what composite functions are. Otherwise, we're going to be completely lost in this discussion. Now, I said that there were two ways to do this. So let's look at a second way of taking h of x and writing it as a composite function. Okay, so what is the second way? We have f of g of x. Yeah, we could have g of f of x. Now, talking about these composite functions, I do think of them as the inside function versus the outside function. So in this case, not only do I see g of x as the input, I also see it as the inside function. And so this would also then be the inside function. Over here, though, my inside function is starting first with f of x. Now, obviously, I'd have to define f of x and g of x to be different than socks, putting on socks and putting on shoes. But we could have functions that we could, define this way. Okay. So what's that got to do with what we're about today? Well, we're going to look at this thing called the chain rule. And the chain rule is actually, just as we chain together actions, like putting on socks and then putting on shoes, we chain together functions. And so our chain here is that we first have f of x and we chain it to the function f of x. So if g of x is my inside function, then my outside function is then, or the last function I talk about, or the last function I do anything with, is then function f. So my chain together here can also look like this. Some of that visible when we talk about the theorem 3.11 or 3.11. So I have y equals f of u. U is what role in function f? It's the input, okay? F of u then represents an output. We can also represent it with the variable y. Now that function is differentiable. A differentiable function of u, again, stating it that way means that u is our input variable. So what does it mean to be differentiable? Eric, go ahead and take a stab at that. The fact that it's differentiable means? Absolutely. You can take a derivative. The derivative exists for it. Okay. Then we have and u equals g of x. Another function, and it is also differentiable, but now it's differentiable function of x. Again, x is the input. We would recognize that if we see g of x, and so it's an input. Y equals f of g of x. Now this looks more like a composite function to us. F of g of x, we saw it up here. The inside function is g of x. The input into function f is g of x. What's another representation of the output g of x? So if I replace the output representation g of x with this other representation, I would have f of u, which is right there. So we are really talking in circles in a way, but the whole thing comes down to this, and let's kind of break it apart. We're using the notation of derivative of dy dx, or the differential y divided by differential x. So dy dx, now what does x represent in this first derivative? X represents the what of the function? The input. So if I have dy dx, then I am actually taking the derivative of this. Well, what's the input here? Yeah, x is the input of g of x, and then g of x is the input of x, and it's in terms of x. So yeah, dy dx would be the same thing as looking at the derivative here. What about this derivative, dy du? What does it refer to? Yeah, the input is u, the output is y, and so it's referring to this because the input is shown as u and the output is shown as y. What about du dx? There we go. Input is x, output is u, input is x, output is u. So what we have then is that to find the derivative of a composite function, we take the derivative of, and I'm going to say it this way, g of x here is inside function f. It is the inside function. So we take the derivative of the inside function times the derivative of the, and this would then be considered our outside function. Put it down here. So the derivative of a composite function is we take the derivative of the outside function times the derivative of the inside function. We're going to work with this today so that by the time you leave, hopefully you'll understand not only how to determine whether or not it's a composite function, but how to determine what's the inside function and what's the outside function. It's really not that difficult. I'm going to show you some examples how we do this. This is really called the chain rule because we're chaining together derivatives, just like we're chaining together functions up here. We actually get this information later on in a theorem called the generalized power rule. It's still chaining together derivatives. Let's take a look. This says the derivative with respect to x of f of g of x. Well, what is the role of g of x in the function f? It's the input, so this is the inside function. Look what happens with that inside function. Can you read that? We take the derivative, yeah. So this is the derivative of the inside function, okay. Up here, which of these was the derivative of the inside function? Du dx, yeah. So this corresponds to du dx. Okay, this piece says take the derivative of f. Now the derivative of f is what we call the outside function. It's literally on the outside of everything. So this then is the derivative of the outside function. So I'm once again chaining together two derivatives. Derivative of the outside function with the derivative of the inside function. Up here, what was our derivative of the outside function? dy what? It was dy du. Okay. Now, if this is the first time you've seen this, it can be a little confusing, so we're going to make sure, again, that we take this apart piece by piece and that we have some understanding of it. So let's go to the next slide. This is asking you to do nothing more than write this function as the composition of two other functions. So take a look at that. And I'm going to write an f of x. I'm going to tell you I want f of x to be the outside function. And then g of x, and we're going to make g of x the inside function. I'm going to stop.